All right, we're going to do the notes on section 3, which is about how to run experiments, how to design them, and how to evaluate them also. These notes are good to listen through because I'm going to add a story through it. So we're going to learn a lot of definitions through this idea, and I've done it as kind of telling in the sentence form to kind of develop the ideas rather than just sit around with definitions. But I will also, at the same time as we start to learn about the definitions, give an example as to how they're used with a single case to help make sense of it. So we're under section 3, experimental design. We just learned about how to design samples. That's all about, there's the population, we want to know about it, we get samples from it. Experimental designs, experiments are different. The way they work is, we think that maybe something is having an effect on something else, or we wonder if something will have an effect on something else. We have to be very careful, because in life we tend to jump to the conclusions about cause and effect a lot. Sometimes where it's obviously not the case, but a lot of times where it's not obviously the case. So how do we actually determine a cause and effect if something is impacting something else, having an impact? We have to design carefully a well-controlled, randomized experiment, and then we can say, this causes that. But we have to be aware in everyday life. Example, we may see outside that, I happen to know this when people carry raincoats and umbrellas, that it tends to rain. So a silly conclusion to jump to, but no less silly than a lot of other ones we come to and say, well, I guess people carrying around umbrellas causes it to rain. And we know that's not the case, but how could we find out if carrying umbrellas actually causes it to rain or not? We would actually develop an experiment, and then we could say, okay, that is actually causing that. But most of the time, we're thinking about observational studies, observational study. So we say, if we want to observe individuals and record them without intervention, we conduct an observational study. And more importantly, without saying, without intervention really is going to mean to us not randomizing treatments. We'll talk about that. So most things we think about are observational studies, whether formally or not. But if we want to examine a cause and effect relationship, we conduct an experimental study, or experiment. The word study in and of itself doesn't necessarily mean one or the other. Now, the individuals on which the experiment is done are called experimental units. So I'd like to bring up my example that I'm going to use this whole time to walk us through in using these ideas. So let's say I think I've created a new cure for headaches, and it's in pill form, whatever it is we don't talk about, it's made up. But I want to see if it works, so I have a bunch of volunteers. We'll say, my class, you're all my volunteers. So the way to work is I'm going to end up obviously giving my headache cure, so called my headache pill, the Craven pill, to you, and we'll see if it can help reduce headaches. So I'm going to run an experimental design, because I really want to see if we can have a real cause and effect. I want to prove that it does help reduce headaches. So therefore, the people would be my experimental units. They're people. And when they're people, we tend to call them subjects. When they're inanimate objects, we tend to call them experimental units. They're always called the experimental units. Realize that's different than saying measurable units, as in, you're used to think about also like show your units, miles per hour, kilograms. It's not that kind of unit. It's experimental units. And it says if the units are people, we call them subjects. The experimental condition we apply to the units or subjects is called the treatment. So the treatment will be the Craven pill. That would be the treatment. We want to see if that treatment has an effect on headaches. The explanatory variable that we're seeing if it causes a change are called factors. This is more the mathematical definition of what we're saying if one thing causes another. Before I go into talking about these two, realize that in the long run, you don't really have to worry about the difference. There'll be no testing format I'll ask you, and people tend to use them somewhat interchangeably, but really think about their treatments. We could also call them the factors. Treatments is usually a more specific. It's the Craven pill. We could just say the general factor is going to be, pill in the case, but treatments will define more. So don't worry about the difference. We call them treatments. You can say or factors. The factors are going to hopefully create a response. Now, the factors may be applied in different levels. Different levels. I have the Craven pill. Maybe the factor is going to be, the treatment would be the Craven pill. The factor would actually be, say, milligrams of this formula, okay? And they could be applied sometimes in different levels. So let's say I want to see, how much is needed and how much of effect it has. So therefore, I'm going to have some of you be taking 10 milligrams and some of you 20 milligrams to see that. All right, so we'll do 10 milligrams and 20 milligrams. Those are the two levels of the factors of the Craven formula. And the treatments would end up being, I'd have some people taking the one type of pill and the other type of pill. So right now I'm thinking about 2 treatments. Now, we are constantly going to be thinking about confounding variables. So I want to bring this up early. I'll bring this up again. But when designing an experiment, we want to minimize the effect of confounding variables so that our results are not biased. In other words, in the end of this is the common sense part, despite all of this setup, is that I really want to be able to say in the end that it's really the Craven pill that's causing the reduction in headaches. I don't want anybody to come back and say, well, it could have been this or it could have been that. Right? Those would be confounding variables because I wouldn't know if it's this or that or the Craven pill causing the reduction in headaches. So let's continue. So here's discipline number 1. Because we may not be able to identify and eliminate all confounding variables, it's essential we use control. That's a big word, control. It's going to be one of our design disciplines. A purposeful, identical treating of all conditions except for the experimental treatment. So really, I want to make sure what I'm going to have is, so far I have some people taking the Craven 10, some people taking the Craven 20 milligrams in there, and I want those people to have everything else the same. I want to have lighting conditions the same, things they're eating relatively the same, sleeping conditions, everything else, volume, of course, everything that might affect headaches especially. So in designing experiments, we try to do is we make a list of all the things we think can make headaches better or worse. We try to make sure all those things as possible are consistent to both groups, as we go. And that way we can say, well, which works better, the 10 milligrams or the 20 milligrams? And since everything else was consistent, we'll say, oh, looks like the 20 milligrams is better. Or maybe there's no difference. So that's control. Now, I want to bring this up because this is very likely what I would use. Sometimes there's also a control group. The control group will get a fake treatment. We probably know it's called a placebo. That way we may make the comparison. So I would do this. I would actually have you broken up into thirds, probably say. So 1/3 of you have taken the 20 milligram, 1/3 are taking the 10 milligram, and 1/3 are taking another pill. All the pills are identical, but the pill actually is, we call it a sugar pill. It has really no effect of any kind. Now realize that's a control group. A placebo group is an element of control because I'm keeping everything the same. That's important because of something called the placebo effect. Placebo effect. So this is important due to the placebo effect, a psychological self-fulfilling prophecy where someone's belief in a change can create the change. You don't necessarily have to take a psychology course to see that this actually is a real thing. People who think they're getting a treatment will often start to feel better. I would say with headaches, that's especially true. So it'd be very important that for control's sake, everybody thinks they're getting the same treatment, and that way they'll have the same effect on themselves naturally. I bring up an example here that you may learn out of taking a psychology course, called the Hawthorne effect. This is an example of something happened. I believe it was a company that created actually light bulbs, coincidentally, or something with lighting. But you can see there's a placebo effect. There's also something called a Hawthorne effect we have to be aware of here. The story goes something like this. There are a bunch of workers, and they wanted to see if improving lighting conditions would help make them more efficient or productive. All the workers knew this was going to happen, and they knew that they were testing to see if the lighting conditions would help make them more productive. So sure enough, they changed lighting conditions, and everybody was more productive. So in the one case, we can call that a placebo effect. They believed they would be more productive, and they made themselves more productive for whatever reason, how that went. Now the Hawthorne effect is actually also something else, because what they happened to find is, so they kept the lighting conditions the same because they thought it worked better, but they found out that after a little while, things tended to go back to the way they were. So the Hawthorne effect is another thing we're aware of, is that sometimes things can seem to have an effect and then it seems to go away, and that is part of the placebo effect really often is the case. So that's what we could talk about when we run experiments. We want to make sure we record data for a while to see what the lasting effects really are in that case. All right, so the next element, the next discipline is randomization. or random allocation, or random assignment. Realize that's very different from random sampling. The only word it has in common is random. But here's what we say: since we won't know all the confounding variables. I can't know everything that's going to affect headaches that could exist, and I can't control for all of them. Even if I know some of them, I can't necessarily make them the same for people. For instance, some things might be genetics, right? Genetics tend to affect people a little differently, right? And I don't know what genes everybody has and how that's going to affect you when it comes to the pills. So I can't control for them. So things we can't control for, we use random allocation or randomization. That's what that term means. It's a method of random assignment of our experimental units to the treatment groups. So what I would do is, remember I had a third, and a third. Who gets which treatment? It's very important that I would let probability, this randomness, decide who's going to be in what group. We learned how to do that already in this chapter. Simple ways could be to mix people up using any kind of random digit table, random number generator, or something like that. You could pretend the idea of everybody's names in a hat, shuffle them up, and I say, this person's in group 1, group 2, group 3, group 1, group 2, group 3. People wouldn't even know what groups they're in, but one group is going to be randomly decided to get the placebo, the fake treatment, the sugar pill. One group would get the 10 milligram, one group gets the 20. Now, this way, the effects of those lurking and confounding variables will somewhat even out, since they'll be equally prevalent in both groups. They should be. Remember, I have people with some genes here and there. I don't know who they are, but hopefully, since I've randomized people to all the groups, I probably have people with both kinds of genes in all the groups. So we say that those confounding variables tend to even out, kind of almost cancel each other out. Like, he has this kind of gene, but he also has this kind of gene, probably, right? Those things are in there like that. So it looks like that. Before I move on, realize this is the one thing that we can actually say makes an observational study become an experiment, where cause and effect can be opened up and discussed. We have to have random allocation of the subjects to the treatments. We can't let them self-select, or we cannot have them just happen to be this way. Quick example, in my room, the window is over here, and it's darker over here. If lighting makes people's headaches worse, people could bring up the common sense idea, well, it might not be the headache pill. You had all the people sitting over here, and they all got the Craven pill. So they got better, but it was actually because of the lighting. It's keys that will randomize everybody to get them all controlled, have the same conditions. But also, even if I'm not aware about lighting, I hopefully over here, or wherever this is in the world, I have some people getting lighting who have the pill, and some people who don't have the pill, some people have the stronger pill. So it just evens out, cancels out, and it works like that. So I say now we'll define it. Beware of confounding variables. Brought this up earlier. Confounding is when one cannot tell whether it is the treatment or the confounding variable that is creating the measured effect. Right? So a confounding variable could have been lighting, and I would say it's confounding because we won't know at the end of the experiment if it's the lighting, right, the confounding variable, or the headache pill, the treatment, that's causing the response being headache reduction. I'll give a famous example here. It's called the nursing home and herbal tea study to show why it's so important that we use the elements of experimental design to try to show cause and effect. A while ago, they wanted to show that herbal tea, see if it makes people, I guess, happier. And you'll find out in psychometrics is the way we can attach numbers to all kinds of things, especially psychologically speaking. We can measure happiness on a scale, say, of 1 to 10. I won't get into that. But they can measure happiness, and they want to see, does taking herbal tea make people happier? And we can measure the happiness on a scale. And the way it went is, I think it was college students would bring herbal tea into a nursing home, and they would give herbal tea, and they'd let the people in the nursing home drink the herbal tea, and they measured their happiness rating before the tea and some point after the tea, and they tried to see, does it have an effect? And they found out, wow, look, they do end up having happier ratings on average after the herbal tea is all done. So therefore, herbal tea makes people happier. And of course, you can imagine all the confounding variables that exist. We name them and sit around naming in class and talking about them, but just getting something for free is nice, makes people happy, right? It'd be smart if they had everybody getting something free, some people getting herbal tea, some people not. Having people visit people, especially in a nursing home, can make people happier, right? Having people visit you, it's really nice, right? So it'd be smart if they had some people visiting everybody, some people getting herbal tea and some people not getting herbal tea, but getting a type of a placebo. They didn't have any random assignment of treatments. They didn't have any, they had one treatment, so that doesn't really work. They had no control, so no comparisons. They had no control because they had no comparison group. They had no randomization where they let some people get the one, some people get the other, let it cancel out. So in the end, it was nice, but they couldn't say definitively, well, yes, herbal tea makes you happier. It's still, well, maybe. We don't really know. So, experimental designs. So I say, remember, if you want to examine a cause and effect relationship, we conduct an experiment. So what, you remember that. We're going to start to use the famous mantra which says, correlation does not imply causation. Just because things are connected doesn't mean one thing's causing the other. However, in a well-designed experiment, we can. So in an experiment, if an experiment is well-designed, a strong association in the data does imply causation, since any possible confounding or lurking variables are controlled. In case I haven't defined lurking variables yet, depending on when you're watching this, a lurking variable is something that we haven't measured and is lurking behind the scenes, and we're not really aware of what it is. Please don't worry about the difference of confounding and lurking variables. Let the common sense approach to what this is all about is saying, I don't want other people to say it's other things than the Craven pill causing the headache here. That's really what it's about. So I can say, if I do, after a certain amount of time, find that people are on average having a better headache reduction on the randomized group with the 20 milligrams than the 10 milligrams, and the 10 milligrams better than the control group who got nothing, then I can say, wow, it really does have an effect. Of course, I might find out with the levels that 10 milligrams and 20 milligrams are both good, they're about the same, and that also helps you figure out what kind of dosages to use later on. Anyway, we call these the three principles of experimental design. Control, randomization, and replication. So let's talk about these. I've mentioned the first two. The third one I hadn't mentioned, although it's somewhat obvious. It's not a real big idea. Control was the first one. We control the effects of lurking variables by comparing several treatments. Sometimes we can include a control group. Basically, we try to keep everything the same. Remember, control is about keeping everything controlled the same except for treatments. Now, some things we can't keep the same. Some things we don't know about, so we have to randomize. Remember, randomization or random allocation is the one thing that actually makes an observational study become an experiment. These three ideas can make it a good experiment or not very good experiment. So we use randomization to assign the subjects or the experimental units to the treatments, right? Randomly, let all other confounding variables even out then. The last idea is replication. Notice it's not repetition. People mix up those words, but it kind of means the same thing. Replication, replication, excuse me, in the sentence form, this should say replicate. So, replicate the experiments on subjects or units to reduce chance variation of results. We call that idea of replication. So, replicate on many subjects. There is something called replicating experiments. That's not what I'm talking about here. We're talking about basically not just doing the experiment on one person or two people. For example, nobody would believe my study if I had one person get the 20 pill, one person get the 10 pill, and one person get the placebo, and I said, hey, look, that one person did better than this person, and this person did better than that person. You can say, well, there are a lot of things that could happen. You only had 3 people. Maybe that one person was going to feel better anyway. There are all kinds of things. So what we have to do is we have to have big sample sizes, right, that we would use. Lots of volunteers, right? And we'll use probability later to show, how does that affect the likelihood of causes, and what does that mean? But really, it would be more believable in, say, a class if I had 10 and 10 and 10. That's a little more believable. Really, that would be a still very small experiment. I'd want to replicate more than that. But it'd be a lot more believable if I said the average of the 10 saw a better headache cure than the average of the 10 than the average of the 10. And then it becomes more believable. So remember, when you think about what makes an experiment good, think CRR in your brain real quick. CRR, control, randomization, replication are the 3 ways that make an experiment run well. So our hope is to find the effect to be statistically significant. It's an important phrase that you have heard before, whether or not you've paid attention or not. You'll hear it and see it a lot now. You'll notice it. That's when the measured effect is too great to be caused simply by chance alone. It's got to be caused by our treatment. Right? We'll have numbers to show when things are probably or are statistically significant. But basically it means, if these people got a little bit better than these people, we could say, oh, that could just be chance, right? A little bit better, eh. But we say, either there's so many people getting better than these so many people, that can't be chance. Or the effect is so great compared to these people, then we often say, well, basically the point where we say, we really believe this is something. We believe we're getting at something. We don't think it's just random luck, right? Random luck helps really dictate what happens in the world more so than anything else. So even a well-designed experiment can still contain hidden bias. That's not one thing. It's just saying bias, that's something causing something to be a certain way, a predictable kind of effect that we don't want. So it's extremely important to handle the subjects of the units in the exact same way. And remember, that's really an element of control doing that. But here's one element of control that's a good idea. One way to avoid hidden bias is to conduct a blind experiment. Blind or blinded, I've seen both phrases, it doesn't matter. Which is where the subjects aren't aware whether or not they have received the actual treatment. So I hinted at this earlier with the one type of blinding, which is where the subjects won't know which pill they got, right? They won't know. It'd be kind of dumb. It wouldn't really be a placebo if I gave you the pill and I said, this is a fake pill. You would think it's the real pill. So you're probably aware of that idea. That's in a blind experiment. So I say it's where the subjects aren't aware. Now actually that's single blind. And there's another type of single blind where it's the person who's interacting with the people doesn't know which pill they had. This is extremely important. It might not seem important. You'd say, what difference does that make? Because people can intentionally or unintentionally affect the way it's going to happen. If I have, especially if I have money or any kind of a hope and motivation in this headache pill working and coming to light, right, going on the market, then I might influence the data somehow or the people somehow, even unintentionally. I might talk more quietly or louder to people and do things differently, make offers and things like that. So it's important we also try to blind the people interacting. We call them people interacting, people giving the pills, but also people measuring the effect in the end, right? That may be the same person, may not. So really in a double-blind experiment, neither the subjects nor the people who have contact with them know which treatment a subject has received. Now realize somebody knows, of course. It's all usually turned into numbers. Subject number 452 got treatment 23, and they had a measured effect of minus 10, and it goes to the computer. And in the end, they can take a look at which, it was this treatment, and they can look at it. But so don't worry, somebody knows, of course, in the end. I think this is where, So I'd like to stop the first part of the lesson. The next part of the lesson we'll go into talking about the three types of experimental design that we're going to learn about in this section. But that's the idea of a randomized controlled experiment. Watch over again if you need to. Think about that story of the headache pills when you're thinking about all these ideas. But it's a lot of vocab. You want to have it well understood.